Okay, optimization part 2. The question is find the point on the graph of y equal radical x, right? That is closest to a point A, 1, 0. We need to find the point on the graph closest to point A. That's great. Let this point on the graph be P, right? Of abscissa x. If the abscissa is x, the ordinate is radical x, is y. Y is radical x, right? Where x is greater or equal to 0 because it's the domain of this function y equal radical x. X is found in the radical sign, so it will be greater or equal to x. The distance from P to A is given by how we find the distance from P to A. We need to find the closest distance, right? P to distance from P to A, it's PA. It's a distance, right? And what is the equation of the distance? What is the rule of the distance? It's abscissa of P minus abscissa of A squared plus ordinate of P minus ordinate of A squared. That is radical x squared minus 2x plus 1 plus radical x squared is x, so it is radical x squared minus x plus 1. Plus 1. This is the final distance, right? Now, the distance d for sure is a positive number. When the distance is minimum, it is minimum if d square is minimum. D square, we remove the radical, which is x squared minus x plus 1 is minimum. So we find, let's take this as f of x, and let's find its derivative. What is the derivative of f of x? It's 2x minus 1. Taking this derivative equals 0, we end up with x is equal to half. Right? X is equal to half. If f prime negative, then x less than half. If f prime positive, x greater than half. We can we can draw the table of variation. X minus it's from 0, right, to plus infinity, and it's half. The derivative of x is 0 as x equal half, positive to the right of 0, negative to the left, and what that gives me for f of x, if x is 0, radical 0 is 0. If x is infinity, radical infinity is infinity. It goes downwards, upwards, positive, negative. And if x is half, this is radical 1 over 2. Radical 1 over 2, which is radical 2 over 2. All right. So therefore, the point on the graph which is closest to A is the point P of abscissa half and ordinate radical 2 over 2. This is optimization. We want to find the minimum value that is closest to a given point. So we found it. It's the minimum point. Let's go to another exercise. Let's go to another example or exercise. Suppose we have a square of each side length 80 centimeter. Let me draw it as square. Suppose that is a square. The length of the side is 80 centimeter, and and suppose we have another square at the end. We cut is another at each end, from each end, another square of side x, right? Each corner we are cutting x, so we can fold this and make a box. So the main square is 80 centimeter, and each one of those edges is x centimeter. That's great. We make a box. What we want to know here, what we want to find, is what must be the value of x. What must the value of x be to produce a box with the maximum possible volume? We need to know what x we should take here, to do the maximum volume of this box. That's great. What is the base of the box? Is a square of side. What is the side? The box, after we fold, after we cut those parts and we fold it, what will be the side of the box? This will be the side of the box, right? And this is 80 centimeter, 80 centimeter minus twice x, because we did cut x from this side and x from this side. That's good. That the height of the box is x, because when we fold it, this will be a height of the box, right? So the length of the box is 80 minus 2x. The height of the box is x. What is the volume of the box then? Volume of the box, we need to find its maximum volume. It's the height times the length again, because the base is still a square, so the width will be equal to the length. And for sure, x is a value. It could be 0, and maximum 40, because we want to cut a part of it, right? So it maximized to 40, right? Half of the 80, right? Because we have to cut x from each side. So what is the volume? Let me expand this. This will be 6,400 minus 4 times 8, it's 3,000. 4 times 80, it's 320x plus 4x, right? Expanding this, and then we do what? The volume is this is x squared, right? Let's multiply the x inside. It will be 4x cubed minus 320 x squared plus 6,400. Now we find we need to find the maximum volume, so we need to find the stationary point. We do the derivative of the volume. It will be 12x squared minus 640x, and the derivative of 6,400 is 0. This is x too, right? I didn't multiply with x here, so plus 6,400. This is the derivative. Let me factorize. We take 4 in common. What we got is 3x squared minus 640 divided by 4. It's 160 x minus this okay, 8 divided 8 times 8 times 800, 2 times 800, 1600. And we factorize also what we have here. This is by guess and check, or by using delta. This will be 3x and x minus times plus, and 1600 is 40 times 40. That's correct, because minus 40 and plus 120, it's this is minus times plus. This is minus times, this is plus, and this is minus times minus. Okay, this is minus times minus. Now minus 40x and minus 120, it will be minus 160. This is the derivative. Taking derivative equals 0 gives me two possible values for x. 3x minus 40 equals 0, right? This means x equal 40 divided by 3. This is one value. Or x minus 40 equals 0. This implies x equal 40. That's good. Now let's find the endpoints, right? Volume when x is 0 is equal to 0, because if we substitute instead of 0 instead of x in volume, we got 0. So we have a point 0, 0. What endpoint? What else endpoint? We have 40, right? V of 40, it will be equal to, when we substitute 40 instead of x, we also are going to get a volume equal 0, because you can substitute it. It will be 0 for sure, because then we don't have a volume. The box will be folded as just a paper, right? No capacity in it. So 40 abscissa 0 ordinate, and we find V of 40 over 3. It will be you substitute it. It will be 37,926 centimeter cube. And what else we have? What is the maximum possible? Therefore, the maximum possible volume is attained when x equal. This is the maximum possible value. Okay, when x